So last class, like we saw what is optimization, why we need optimization. One example I gave you is from A to B, from your starting point till your destination, you might have different routes. Google Map gives you different routes, and it gives you the best route, okay, to choose. Suppose you are leaving the institute at 5 p.m. and then you see to your home what are the possible routes. And if it is via the main road, then you can know that, yeah, it might be busy, and Google says you that going through this route can cost you 30 minutes or 20 minutes extra than your normal route. So the shortest one, like shortest route in the sense that which will take less time, right? So therefore, that's like an optimization. What's your like what you're optimizing here? You're optimizing the time to reach from your starting point to your destination. So what is your objective function here? So the function you're trying to minimize is known as the optimization function, like objective function. Okay. So what's the objective function here? Time is the objective function. Or maybe the distance can also be the objective function. Okay. Time, like which measures the time, which depends on the time, like formulating the time, are known as decision variables. Okay. So those are the variables that are inside objective function. Those are known as decision variables. So before starting optimization, like you know about non-convex functions, is it? Convex functions, convex sets. So first of all, why we will bother about convex sets or convex functions? Why we can't live without them? Okay. So whatever optimization techniques you will learn here are only for convex functions. They are not for non-convex functions. Okay. Apply to all kind of functions, but some only to convex functions. So optimization methods, the numerical methods for optimization work very nicely and efficiently in case of convex functions. For non-convex functions, the methods are pretty hard. That we will not be covering here. Okay. Our idea is, so therefore those methods, those optimization methods which can be applied to convex functions are known as convex optimization. All right. Convex also, some books you might see convex optimization. That's optimization only, but you are applying optimization to convex functions or convex functions. So what is a convex function and how it is different from a convex set? Okay, so first comes convex set and then comes convex function. So what is a convex set first of all? The idea is like, let me write here. So convex sets. So the idea is like, say if you have a straight line, you have a straight line, take any 2 points on that straight line, say A and B, then I'm saying that whatever convex combination you take in between these 2 points will always lie in between A and B. Okay. What does that mean? Convex combination. Convex combination of A and B means collecting all the points which are in between A and B, which are in between all this, like all these points. Okay. So that's like convex combination. So how can we write it mathematically? Can you think? How about like this? So this is an abstract way of writing, but this is so nice. Why it is so nice? Put lambda equals to 1. Put lambda equals to 1. What you are getting? A. You are getting A. Put lambda equals to 0. What you are getting? B. Isn't it? Understood? So you understood it. If I put the lowest value A, and if I put the maximum value of lambda, which is 1, I am getting B. Sorry, if I put lambda equals to 0, I get B. And I put lambda equals to 1, I get A. So extreme points are within A and B. So any lambda in between will make the point X lying in between A and B, right? Are you getting the logic behind this? So this is known as the convex combination. Why the convex combination? I could have written this as P and this as Q. Okay. where P and Q should add up to 1. That's the convex combination. So you see lambda and 1 minus lambda, they are adding up to 1. So such quantities P and Q which add up to 1 make the convex set or a convex combination. Okay. So this is a convex combination. I would say my experience here, like sometimes what happens is in your projects in your research projects, you will be having these 2 points A and B. Some method you might think of, you want to construct this A and B. Okay, but then you don't know, if you don't know the idea of convex, apply to it. You can't apply in coding way. Okay, so before I learned about convex combination, I had already applied convex combination. I'm saying about my experience. Okay, so I needed a straight line in between. I needed a bunch of points. I had points A and B. So this is one of my coding for research projects. So A and B I took. Then my project asked me like, can I take a 1000 points in between A and B? So then I thought, how can I take 1000 points in between A and B? But at that time, I was not knowing about convex combination. So intuitively, I applied like, if a point is lying here, then it should be a fraction of A. Those kind of techniques I had applied. Later, I came to know that the idea is actually coming from the convex combinations. Okay. So what I will do, need 1000 points in between A and B, then you can random 1000 random values of lambda. 1000 random values of lambda in between 0 and 1, you will generate 1000 random points in between A and B. Is it intuitive? Okay. So without even knowing any formula and just using intuition, you can generate 1000 points in between A and B given to you, any points. So that's why I'm saying this statement has a lot of power. Especially, it helped me a lot. Convex combination. Okay, so this is the informal definition, but maybe I will write a formal definition here. Uh, so this is a straight line. So a straight line is a very nice example of convex sets. Okay. I'll write a formal definition here. Say your convex set is denoted by C. Suppose C, I'm calling it as a convex set. A set C is called convex if the line segment in any 2 points C so lies inside C. Or like what are the 2 points? Say these 2 points are say x1 and x2. So say for all, so this is the symbol for all. Okay. This is the symbol for all. So this, or if you can write for all. Okay. The mathematical notation. All x1 and x2 in your set C. Okay. Also say like theta or lambda belongs to 0 and 1. I can say that same thing which I have written above, theta x1 plus 1 minus theta x2 belongs to C. So this is the symbol for belongs to. Okay. Still not understood it. Same definition I had applied. Instead of lambda, I have taken theta. So you can take anything you like. So what it is saying, any points. So this A and B are not any special points. Any point A and B you take on the straight line, any point for A and B, convex combination, the points should lie in between A and B. Okay. then only it is a convex set. Now, visually seen what is a convex set, but what is not a convex set? That also you should know. Okay. Any example what is not a convex set? Any example what is not a convex set? Is this a convex set? Set C, a convex set. How you can see? Take any 2 points. I took, okay, this point and this point. Take any 2 points. Okay. What will happen? If you take any line segment joining here, okay, do you see all the points are lying inside the set C? Can you visualize this? So take any point A and B. It is not that difficult. Take any point A and B. Okay, take a convex combination between them. Okay. So all these points will lie inside this, right? But these are the convex combination points, right? And where they lie the inside set C, right? What's the issue? Yes. And A and B should not be fixed. It can be any point A and B. It should hold for any point. It should not be that it holds for only one point. It should, if it is to hold at any one point, it is not a convex set. Points. Similarly, you can take A and B, these two. Every time it will hold. All right. Okay. So what is not a convex set? So you know this is a convex set. What is not a convex set? Do you think this is a convex set? So it is a convex set, okay? Yes. How many of you say it is a convex set? So set C means what is this set C? This means that it is constituted of a million of points, like a lot of points. You should not get afraid seeing that cartoon. So how many of you say it is a convex set? How many of you say it is not a convex set? So say like these 2 points I take A and B, then you take convex combination of them. So every point lies here is also lying inside set C. So it is a convex set. Okay. Should be have it should satisfy for take and this point at B, and you take the convex combination of A and B. There are of course some points here lying inside the set C, but there are also points which are not lying inside set C. And these are those set of points. Okay. So therefore, this definition is violated, right? This definition is violated. Theta x1 plus 1 minus theta x2 belongs to C. You see that these points, even their combination, they are not lying inside set C. Hence, it is not a convex set. Right? So some of the examples for you to think: a singleton set, a line segment, or a straight line like without like extending to infinity, okay, are all examples of convex sets. Okay. Even empty set phi is a good example of a convex set. Okay. So think about why it can be a convex set. But what is a convex function? You learned about convex set, but what is a convex function? So again, we will borrow the ideas from the convex set to define convex function. All right. So I will write the definition here. With it, like it might appear a bit abstract, but so say like that convex, that function f, a function f is said to be a convex function if something happens. All right. So it can be taking your input from n dimensions. Like it can be a function of n variables, x1, x2, x3 up to xn. That means Rn is there. That's the domain, right? Yes. And suppose it gives you only one dimension output, that is a real number, that is only R. Yes. So it is taking input from n dimensions and only splitting out one variable, like one value or something. That's like not a real one. This is said to be convex, like your function f is convex if like very basic, like you should know the domain of the function. Okay. If its domain is a convex set. Okay. So a function is said to be convex if its domain is a convex set. And you know what is a convex set. All right. So if function f is said to be convex, if the domain of the function is a convex set. So that means like for all, same definition, for all x comma y in belonging to the domain D, say the domain is D. And also we have a parameter that is lambda, like 0 to 1. We have this quantity, like your function evaluated at the convex combination, that is lambda x plus 1 minus lambda of y is less than equals to lambda of f of x plus 1 minus lambda of f of y. All right. So there is a very nice intuition. There are two intuitions behind this statement, which I will communicate to you, and after that you can appreciate this definition a bit better. It means that if we take any 2 points x comma y, okay, x comma y, then f evaluated, the function evaluated at any convex combination, f evaluated at any convex combination, meaning it is, he is saying about this. This is the convex combination between x and y, and you are evaluating f at the convex combination should be no larger, okay, than the same combination of fx and fy. Okay, the same convex combination of fx and fy. You're getting the function evaluated at the convex combination of the points x and y should not be than the convex combination of fx and fy. Okay. So geometrically, like if you want to understand this geometrically, the line segment connecting, like let me draw this so you can understand. All right. So you have a function which is f here. This is your function f. So you have a function f, you can see on black, that's the curve. And I'm taking x and y 2 points, any 2 points. Okay. So you can see it is applicable for all points x and y. So this x and y, it need not be only one choice. It can be any choice, like, yeah. So what it means geometrically, the line segment connecting x comma fx, which is this point, and y comma fy, okay, must sit above the graph of f. Okay, this line segment is sitting above this graph, isn't it? Yes, between these 2 points. Like, forget about this line segment. We are only interested in between these 2 points. Is it true that this line is lying above the black line, black curve? Yes. If it is so, then f is a convex function. Okay. So the line segment connecting your mm, connecting x of fx and y of fy. Okay. Uh, Lie above graph of f. That's the geometric interpretation of a convex function. Can you see it from here? Can you see it from here? F of lambda x plus 1 minus lambda y is less than equal to lambda of fx plus 1 minus lambda of fy. Okay. So that's the geometric interpretation. Like you take fx, you take fy, and then you connect the line in between them, the convex combination line. That curve must be above the curve of f. That is so, then your function f is convex function. So I gave you an example of what is a convex set, and I also gave you an example of what is a convex function. All right. And there is one more concept before we move, which is like unimodal functions. Okay. Unimodal functions means the function will have only one minimum or one maximum. Okay. Bimodal means you have more than one. Right. So convex functions, whatever convex functions you take, they will always be unimodal, but not the other way around, is it? But not the other way around. So convex functions are unimodal. Okay. Sure that this is not other way around. You can't say that all unimodal functions are convex. Okay. So all convex functions are unimodal. How? Can we see this example? So this is a convex function f here. You can see it has one minimum, right? Which is here. Yes. So therefore, it's a unimodal function. Take a unimodal function and say that it is a convex function. Okay. Yeah, because I will say this is point number one, because there are unimodal functions. Try to check it if you're interested. There are unimodal functions which are neither like convex or like concave. All right. So these are the basics you might need in this optimization module. See these terms interchangeably. Convex optimization, consider a unimodal function f. Okay. Whenever you will be reading something, come across these words. So there are a lot of different definitions like convex set, convex hull, convex polygon, many different terminology. If you are really interested in optimization, then you should be learning about all this. Okay. As you know, a function, like any function, not a convex function or anything, I'm saying a function. That means it can be in general. So a function can have multiple maximum and minimum, no doubt about it. Okay, it can have. Okay. In that case, the idea of local versus global optimum comes. Okay. There will be one local maximum, one global maximum. So here the concept of like local and global maxima comes if your function have more than one maximum. Okay. So what is a global minimum? It's the minimum of all the minimum of all local minimums. Okay. So you have something like local minimum, which is you know already. What is global minimum? So global minimum, what is a global minimum? Well, so it is the minimum of all. Yes. So that's the global minimum, right? So just for an example, like you can see, you have these two, like x and y, all right? And say like I'm drawing a function over here. Can you see which is local minimum here? So as you can see, these are your local minimum, okay? Local minimums. Look, of course, this is also a local minimum, but like smallest of all the minimum, this is known as a global minimum. According to what I drew, that means this should not be local maximum, because you can see this curve here is more than the left hand curve, right? This is bigger than this one, right? So this should be full max. So for convex function, which you already know, local minimum is the global convex function, because for convex function, it is a unimodal. Whatever it has, maximum or minimum, only one of them it will have. Okay. So therefore, the local is the global. Understood. When you have local and global maxima, if there are more than one, you're differentiating it, right? But if you have only unimodal function, then the local and global are the same. Global minima. Okay. Okay. So yeah, and these convex functions are very much like important in engineering and science. So therefore, lot of application and lot of methods are being developed for convex functions. Therefore, you no longer, or like very often you don't see non-convex optimization. You normally see convex optimization. Okay. So therefore, like convex, you always need a convex set or a convex function. Again, so some notation before we start reading about methods. Yeah. Something like this is a notation. Quite often, like I will write something like this arg max or like arg min. What does it mean if I write like this? So the arguments of the maxima, okay, arguments of the maxima, it is abbreviated as arg max. Of the maxima. Arguments maxima. So the short form is argmax. Similarly, argmin is the argument of minimum. Okay. So what are these? What are these? These are like the input points at which the function output is either minimized or maximized. Okay. So these are argmax and argmin are the x values. Okay. Are the x values. They are not the y values. Okay. They are the collection. They are the arguments of the maxima. Argument means the input, not the output. Okay. So these are the input points. So these are the input points at which your function, like maybe the objective function, I will say, the objective function is or minimum. Got it? So it's other way of saying that is the x points okay, the x points at which fx has maxima or minimum. So that's what I mean by arg max or arg min. All right. So we will use this soon. All right. So there is something like optimization, like different kinds of optimization you will see. So those are known as like constraint optimization, unconstrained optimization. Okay, what does it mean, constraint optimization? So have you learned about linear programming a bit? How many? Linear programming. So there is something known as like unconstrained optimization. Optimization. Yes. So in constant optimization, like say, it will say like minimize fx, minimize a function fx given that, like suppose this is function of x and y, given that x plus y is less than equal to 0.5. So this is a constraint optimization problem because it is not only asking that minimize fx. It is asking you that minimize f of x comma y, not in whole of R2 plane, not of whole of R2 plane. Suppose x and y, visualize this as R2 plane. He is saying minimize the function f or maximize the function f. If I say, so I will tell you two things. Problems for you, 1 and 2. First one is saying maximum of f of xy. It is already given to you what is f. The second one is maximum of f of xy given that x plus y is less than equal to 0.5. So the first one, maximum of f of xy, means that you find the maximum of f on the whole of R2 plane. On the whole of R2 plane. For all of x comma y in your R2 plane, find the max of f of xy. That's what it means if I am saying maximum of f of xy, right? So it will take all the points in your R2 plane and compare and find which one is the largest for maximum. Now I am saying maximum of f of x comma y given that x plus y is less than equal to 0.5. Straight line. So x plus y equals to 0.5 means this is your straight line and it is saying x plus y is less than equal to 5. How can I say it is either this side or that side? Simplest way, take the origin as your best point. 0 plus 0, so 0 is 0.5. So therefore, what you can see, this whole side. So you understood the difference between the two of the things, optimization, unconstrained and constrained. In unconstrained one, this is your first, this is your second. In unconstrained one, you play. But in the second one, searching only below the straight line. Okay. There might be some maximum here, but you can't say it is a maximum because you already gave this condition. Because you gave this condition, it is known as a constraint optimization. So now you know what is a constraint optimization, what is unconstrained optimization. Okay. Constraint optimization you have learned in your bachelor's. As you have raised your hands, you have learned in your bachelor's like simplex method or graphical method to find a different maximum and minimum of functions. But what about unconstrained optimization problems? That's what we will deal in this module. It will be fully on unconstrained optimization. Okay. Remember about argmax and argmin, right? So let me write the example quite formally. Like global minimizer and local minimizer. Okay, that means say a global minimizer. Global minimizer, like it's the input point, and I am giving a special notation to it, like X star, and it can be like 1D, it can be n dimensional. That's the beauty of this method. Okay, you already know for 1D, it is quite intuitive. But if you go to higher dimension, it might be that for a given long data set, like this is the long data set, 50 dimensional data set. Okay. Can anyone give any example of this? If you are higher than 3? Rainfall depends on, can anyone model rainfall? Not yet till now. Okay, but it depends on a lot of different parameters, at least 10 or 20, at least 10 or 20, more, not 3 or 4. Okay, so in that way, it is a higher dimensional problem. In those kind of problem, how to maximize the rainfall? That's an optimization problem. How to maximize the quantity of rainfall? That's all we need, right? May not be in Kerala, but outside other states. Okay, so maximize the rainfall in a particular location. For that, you will have a lot of different variable and parameters, and how you will optimize. The idea of vector comes in. So here X star is, you might be thinking in your mind that this is just a real number, but no, it's an array. It's an array of values. And in math terms, an array is like a vector. So you will see this line over here, the arrow over here. X star is a vector. Okay. So those X star, global minimizer, that means argmin. Okay, argmin, that means you're scanning over all of X and you're taking the fx. Okay. So the collection of all X for which fx is minimized, that's denoted by X star vector. Okay. That's the global minimizer. Can you define global maximizer? Same. Maximizer. Say Y star vector, that's like argmax, right? Understood, is it? Any issues till now? So why it is quite intuitive. It is not that we don't understand this, but the what I want to say is like the importance of this method is about the vector notation. For a higher dimensional problem also, you can write this equation. Okay, just write the vector. Here vector, here everything is vector here. If you are on a higher dimensional problem and you want to optimize it, you can write in this way. Okay, that's what I have written like this. So something I already told, but I again will cover it just for your sake. So you will have a function where which you want to optimize again. That's known as a objective function. Okay. as the objective function. And of course, the objective function depends on some variable x and more than one. So I'm writing as a vector. Okay. And those x are usually known as the decision variables. Okay. So these are the terminology for you. So sort of terminologies. So you want to optimize the function f, then f is known as an objective function. Okay. And the objective function depends on some variables, and those are known as the decision variables. Okay. It's not quite often you don't say the input. What is the input? You should say what is the decision variable here. Okay. And usually this optimization problem is subject to constraints. If this optimization, if subject to constraints, if it is subject to constraint, then you know now that it is a what kind of optimization problem? So subject to constraints means, so this is a which type of optimization problem? Huh? Which type of optimization problem? Subject to constraints like of this form, you might see this is just an example. So this is one of the constraints you might see, like less than equal to constraints. Okay. So what happens here is what is the purpose of keeping an I here? It says that there might be a lot of inequality like this. So here we have an inequality, not an equality. Okay, like I gave you an example, x plus y less than equal to 0.5. So here we inequality. So this constraint is an inequality related constraint. Okay, this is an inequality. All right. And also sometimes you can have of this form. And this is an equality, right? So these kind of constraints you can have. You can have an equality constraint, you can have an inequality constraint too. So such kind of optimization problems are known as constrained optimization problems. Unconstrained optimization problem, obviously, I have not mentioned it here, but you can mention it. I maybe span through M and say J can span through N. So you have totally M plus N constraints, isn't it? M plus N constraint. Now what it means to be a unconstrained optimization problem. So unconstrained optimization problem, optimization problem occurs when M equals to 0. Sorry, M equals to 0, N equals to 0. Is it clear? If you have M equals to 0, N equals to 0, then there is constraint. Yes, because I is going from 1 to M. So you are already setting M to 0. So so there is no constraint. So that means there is no constraint involved. In that case, it is known as an unconstrained optimization problem. So, and you must have heard some terms like linear programming. Linear programming. How many of you have heard this term? Heard of this term, linear programming? So 3 students. Okay. So here, what is a linear programming? Quite often see this word linear optimization course. Okay, a linear programming course. There is a separate course in their bachelor's. In your bachelor's might be on linear programming, where you have where you do this maximizing, minimizing on graph paper. Okay, so here a linear programming, if your objective function in those kind of optimization problem, your objective function and your constraints are linear. All right. Your objective function and your constraints are linear. It is a linear program problem. Then what is like a then I'm talking to you about quadratic programming, and then I'll talk to you about the nonlinear programming. What is quadratic programming? Quadratic programming, your objective function is quadratic. Okay, your objective function will be quadratic. However, objective function is quadratic, but still the constraints okay. So in quadratic programming, your objective function is quadratic, but your constraint will be still linear. All right. So the what is non-linear programming? What is non-linear programming? Non-linear programming is all other cases. Okay. Whatever is not covered in the two, all other cases. Okay. So you know about linear programming now. Your objective function constraints are linear. Quadratic programming, your objective function is quadratic, and but still the constant are linear. Non-linear programming, all other cases. Okay. Whatever other cases you can fit into will be non-linear programming. So something about minimization and maximization, I will tell you. Yeah, this is just a very low. Okay. So say like here is your x and here is your y. All right. I'm giving you a function f which looks like this. Suppose this is your fx. I'm asking you like what is the maximum of this fx. So what you will say? It is surely at the top, right? Then I'm asking, can you plot minus of fx? Can you plot minus of fx? How it will look? It will be totally symmetric. So symmetric around the x-axis. So it will be just okay. So this is your minus of fx. Now I'm saying to you, this is your maximum of fx, okay, max of fx. And if you draw the same line, okay, so what is happening here? This is your max, this is your min. So what this tells, what this geometric interpretation tells us that to minimum of some g of x, where g of x is equal to minus f of x. Yes. So this is one of the problems. Like sometimes what happens is it may be easier for you to do a negation and take the minimum of that in order to find the maximum of that function. If you want to find the maximum of a function, take the negative of that function and find the minimum. Then it is like finding the maximum of that function. Okay. Things. So one of the special cases we will take till now, whatever definitions I have told you about, it's all have vector in it. All are having input as a vector, x a vector, y as a vector. Okay, all inputs were vectors. Now I'm telling you a special case, a very special case, which I think we will focus on this class as well as next class, is 1D. So you till now, like these are n-dimensional optimization problems. Okay, first method we will learn is on 1D optimization problems. So this is a special case and also the simplest case. Special as well as like simplest case. So when x is also a scalar, previously x was vector, right? Previously x was a vector. Now I am saying this is the simplest case we are considering where x is your scalar. All right. So scalar means x is a real number. Whatever we are doing it, it will be on 1D, real line. All right. So take this for now, like x and y are real number. Function f in your case is also going from real to real. So such problems are called like, see any constraints here, right? So it's a unconstrained problem, unconstrained optimization problem, and it is on 1D. So what we say? So this is a 1D unconstrained optimization problem. Okay. Why it is 1D? X is belonging to real numbers, and there is no constraint involved, so it's an unconstrained problem. So single variable unconstrained optimization problem, and of course, like what is our aim? Aim is to either minimize or maximize f of x. That's our main aim as usual. Suppose like fx is a 1D function here, and your decision variable here is x and y. Those are also real numbers, like 1D. Is it clear? So for like how you define an extrema. See, extrema is further classified as minimum or maximum, right? So how you find extrema first? In 1D, one-dimensional problems, not even ND. So this is the beauty of the problem. 1D, you know derivative will work. Then in n-dimensional, you do an analogy of the derivative that's known as an Hessian. Okay, I think some other classes, Hessian. So Hessian we will take when we are doing n-dimensional problems. Okay, when you have more than 2 or 3 dimension, you will see slowly I will replace the derivative. All are same. Believe me, all are same. The notations and all are same. The derivative, you will just replace the f prime derivative with the Hessian. That's it for ND. So therefore, to understand ND, 1D is essential. Okay. So therefore, we are covering one-dimensional examples here in this module. Okay. So can you tell me how for a 1D function, f, how we can find the extreme? Huh? Confident interval? Derivative equal to 0. That's it. Both at maximum and minimum, your derivative is 0 at that point, right? Yes. So what happens if f prime of x star equals to 0? That is like x star is your extrema. There is also another word to it known as a stationary point. That means at that point f is 0. 0 means no velocity, you stay there like a stationary. Okay. By computing f prime x equals to 0, you find the extrema and you check the double derivative. If your double derivative is less than 0, it is a maxima. If your double derivative is greater than 0, it is a minima. Yes. For one dimension, you know these concepts. Already told, like a maxima, like x star now will be a maxima. Okay. If f double prime of x star is less than 0, then a minima if f double prime of x star is greater than 0. Yes. Now, what I ask you to do is like maybe you can visualize this. Maybe as a plotting exercise. Say like you take y equals to fx given by this polynomial like equation ax cube plus bx square plus cx plus d. Okay, and then you choose different variables a, b, c, and d, and then you plot it in Python for those variables and take like the derivative, plot the second derivative and see where it is less than 0, greater than 0. And appreciate that it is either where when you have minimum, you will have the second derivative greater than 0, where you have maximum, second derivative is less than 0. Okay. So those you have to like plot and see these kind of things. Okay. To appreciate the theory better, try to plot any A, B, C, anything you take. Any number, 0.1, 0.5, 1, 2, 3, whatever. I have just told you how to do it in Python, but if you want to solve it analytically, if you want to find the stationary points, how you will find stationary points here? What you will do? Hmm? To 0. So what you will do? You will take f prime of x and set it to 0. So if you set f prime x equal to 0, it will be like 3ax square plus 2bx plus c equals to 0. And from this you have to find x, right? What is the value of x that satisfies this? Is it true? Then this is a root finding problem, right? This is a root finding problem. Again, you have to take help from your previous semester course. Newton method, bisection method, or whatever, like to find the roots. Okay. So what I am saying to you is an optimization problem has been converted to a root. So to better appreciate also, this is one example. Another example is how you can find root 2 via optimization. Can you find root of a number via optimization? If you want to find root 2, how can you find root 2? Any ideas? What you can do is maybe take the x square minus 2 and square. Okay, this is your function f. Find the minimum of this function. What is the minimum of this function? What value it will be minimum? That is the root. Okay, that is the root of that is the root you are going after, right? Yes. So therefore, you could, if you minimize fx, the answer will be the value of root 2. Okay. So therefore, I am saying to you that an optimization problem can be converted to a root finding problem. Okay? Like you can see like a gradient descent problem like optimization method can be applied to regression. So all these methods are highly like very interconnected with each other. Okay. So I think much of the basics are done. Yes, so much of the basics are done. Now I can start with a method, okay? Okay, so we'll start with the Newton-Raphson method to, what do you call, like, there are a lot of methods. There are a lot of methods to optimize a function, okay? There are few methods like Newton-Raphson method, as you know, will involve derivatives. Is it right? Is it right to say that Newton-Raphson method will involve derivatives? What is Newton-Raphson method? If you remember, like it looks like this, right? Does it look like this? If f prime of x is, okay, this method will fail in those problems. Okay, but the most important thing is this method assumes that a function is differentiable. It already assumes that the function is differentiable. If the function is not differentiable, you can't apply this method. Yes. So therefore, like there are some methods. So this is like a very important point I'm telling to you. Optimization methods till now, Some will involve derivatives, some involve derivatives, okay. Some involves derivatives, and those are like your Newton-Raphson method, which you will see now, and also like maybe gradient descent method, and even I think yeah, BGFS and all those method, I think one group will cover. So those kind of methods. But there are some methods also which doesn't involve any derivative. That means you can feed in a derivative, not a function which is not differentiable into that method. Okay. So doesn't involve derivative, does not involve derivative. There are some method which does not involve derivative. Those are like, some of them are like random search method. Okay. And also one is golden search. Okay. Golden section. I would say. Golden section method. Okay. So these are the two methods you will see. One is optimization method, like which involves some derivatives. Then these are like Newton-Raphson and gradient descent. If it doesn't involve derivative, these will be like random search and golden section method. You will see why I'm saying that. But now know that if your function is not differentiable, you have some method to opt. Okay. If you have some function which is differentiable, you can always opt to these methods. Cover now. This will cover next class. Okay. Okay, so Newton-Raphson method is very similar to like the root finding method. Okay. So just keep an eye on the method, like we'll go step by step. So what is our goal? Our goal is, given a function f, right? Given a function f, we want to find x star, that is like either argmin, like argmin or argmax of f of x. Okay. Is it true? We want to minimize that function and we want to find at what value of x the function is minimized. That's obviously the goal of our problem, right? And we want to do this via optimization, like Newton-Raphson optimization method. Of course, what first we shall do? First, we should take an initial guess. That's the very first step. Okay. So take an initial guess. So begin with an initial guess. And with initial guess, say like x0. And then you keep on iterating. So you will have x1, x2, x3, and so on. Okay. So here we will have two more. Like usually you have a step size. Usually you have a step size. Okay. In every numerical method. But in this method, we will have one more quantity that is known as a direction. Okay. That is known as a direction. In which direction we shall proceed. Okay. So in order to motivate this better, I would give an example via a graph. Suppose this is your function, like this is your function f of x, and we are trying to minimize it. So suppose you visually already know that this is your minimum, okay? And suppose you took an initial guess which is lying somewhere here, x of 0. Then what shall be your next initial guess? How it will decide? Should it be on this side or should which direction should it go? We need to have a variable which in every iteration which direction to go. Okay. If it goes this direction, the method will obviously fail. Why? Because the minimum is here. You're going there. Okay. So therefore, like you have to find a. If you go in this direction, if your initial guesses further iterates are in this direction, then very high chance that you will hit the minimum. Okay. So therefore, in addition to the step size, we will add a direction variable in our method. That's the motivation to add a direction variable, which will tell in every iteration which direction should the next iterate should move. concept. So therefore, there is a motivation to add another variable. Okay, now you will see another variable in this. So this same concept will be used in gradient descent. The same concept. Okay. In many optimization method, similar to step size, you will have a direction variable. Okay, which direction it should go. This is a one-dimensional problem, hence it is easy. But like think of a 2D problem on XY plane. Okay, and you have a minima somewhere here. How in 2D plane it will decide where to go? So you should have a direction. So direction is very important. Direction variable is very important in optimization methods. Therefore, in Newton-Raphson method, it will be very similar to the previous one, but you will see a direction variable. Okay. So we will introduce D naught. This D naught indicates the descent. Okay. This descent word comes from the gradient descent. Okay. Descent, or I can use the another word like search and then travel towards it. Okay. Search for the minimum and then travel towards it. Okay. So that's like the work of the variable D naught. Okay. Of course, H naught, and I missed the word direction. H naught is obviously the step size. Okay. All right. So I will tell you one thing. Just let me know. So I gave you an example, like X naught is here. Suppose you started your initial guess here. Your next iteration, suppose it is here somewhere. Okay, that is X of 1. Okay. Then this quantity here you are seeing is the quantity of H naught and D naught. Okay. This is the quantity. All right. How much you have shifted? How much you have shifted along x-axis and to which direction you have shifted? Okay, that is the H naught and D naught. Can you intuitively think this? D naught, suppose it is negative. Suppose here D naught is negative, which it should be. Then H naught D naught is the right place, right? If D naught is positive, H naught D naught should be right side of X naught. You are seeing that concept around, right? So you should think this. You should exercise your brain while I'm explaining, else you will not get. Okay. So now we will have two important points to discuss. Okay. Now we'll have two important points to discuss. Based on that, I will write a formula for D naught, a generalized formula. And it is very, very common sense based. Okay. So what I want you to is carefully visualize the function I drew. Okay. Suppose if f prime at x equals to x naught, okay, that is at your initial guess, is greater than 0. What does it mean? If x at your initial guess is greater than 0, what does it mean? It means your f is increasing, right? If derivative is greater than 0, it increases, right? That's the very first definition of derivative. Okay. Sorry. So if f prime of x at x naught is greater than 0, your function f is increasing. F of x increases with x at x0. Okay. Then, and you are finding f x. Yes. Then where should be your direction? Then where should be your direction? Think about it. Should it be on the left or should it be on the right? I will tell you once again. If f prime of x at your initial guess is greater than 0, then that means your function is increasing as x is increasing. Okay. Your job is to find the minimum of fx. So where should be your direction? Where should the next initial guess should be? Should it be on the left or should it be on the right? How many of you are saying left? How many of you are saying right? How many of you are saying right? Right. Very, very important step here. I want you to understand. Okay, so I'll tell you, I'll explain more. X naught is here, right? If you increase your x here, f of x is obviously increasing. Okay. Do you want your next step size to go in this direction? Yes. So move towards the left. What do I mean by move left? Apply your common sense. What do I mean by move left? By I mean by moving left, I mean x of 1 is less than x of 0. Is it clear? So now you can see whatever basic common sense is there, we are just writing in terms of math. Okay. So sometimes you should not get afraid of these variables. It's all about common sense. Yes. At your initial guess is less than 0. That means f is decreasing with increase in x. Of course, this is not the case for this example, like which I have shown in the sketch. Okay. Then where should be your next guess, like next direction should be? Should it be left or right? Obviously right. Okay. By right, what I mean? By right, I mean x1 is greater than x of 0. Yes. Now, can you give me a formula based on these two observations? Just based on these two observations, you can write the formula for the direction D or D naught, whatever. Can any hint? See, if f is increasing, that is positive. Suppose positive, right? F is increasing means f prime is greater than 0. Positive. When we are moving left, yes, left is like, say right is positive direction, left is negative direction. That's the concept of vector, right? So if f is increasing, f prime is greater than 0, you're moving left. That means d naught is the opposite sign of f prime. Are you getting? No? Okay, what I can do. Um, f prime of x is greater than 0 where you're moving left. Yes, this is positive, left is negative, right? If f prime of x like is less than 0, that means negative, where you're moving to the right. Right means positive. So whatever your sign of f prime is, the negation of that is used, right? So D, the direction vector, minus of f prime, you can set. Okay, you can see from the intuition, right? Why we are using this. Yes. So therefore, like what you can use here, so you can use D to be minus of f prime evaluated at x naught. Okay. So you got an idea here, right? Of the direction where to move. Okay. So yeah. So now you know that what is the concept of the direction D based on inputs. Now we will start with the method. Okay. Now we will start with the method. So we begin with an initial guess x naught. Then what we do? Our job is to find x of 1, right? X of 1 should be x naught plus you have to say which direction I have to go plus how much I have to go. Yes, which direction I have to go, that is managed by D, and how much I have to go, that is given by the step size. So you can intuitively think like it is H naught and D naught. Okay. if you multiply those two quantities, you are taking into account all the things. Okay. I d naught, y d naught, y naught d naught by 3, y naught d naught by 4, or d naught square. That thing you can get easily from this. Think d naught is your minus of f prime. Minus of f prime evaluated. So you can think of it as a tangent. That you think. That is a visual assignment for you. That is a visual assignment. Okay. D is minus of f prime. Okay. F prime you already know. F prime is a tangent. Okay. So you can think now where it will go, why I am writing in that way. Okay. As you know already, what is D naught? D naught we say like it's the descent or search or travel direction. Okay. Not easier. Not is your step size. So whatever we are doing, like we hope, whatever we are doing, like we are iterating the method, right? It's an iterative method. What should be our aim? Our aim should be that f prime at x equals to x of 1, not necessarily x1, but further iterates, should be minimum, right? Like should hit to 0. That's our aim, right? To find the minimum or like extremum especially. Yes, should be our aim. Yes. So keeping this in mind, this is the sole step to derive the method. Okay. What does it mean? F prime x equals to x1 equal to 0. What is x1? I have already written it here. Can you put it here? F prime of x naught plus h naught d naught equals to 0. Okay. Now we are stuck. Now how to move after this? Ideas. Now it should be very clear to you what to do next step. If something is equal to 0 is giving, then what you should do? Hmm? What you should do? You know it. Ideas. Still. See, it should be coming to your mind. We are doing something like this. We are doing something like this. So how you move after this line? Series. Okay. We use Taylor series. You already know it. Yes. Mostly in the starting of the course, this course we used f of x plus h and f of x minus h. Then we added them and we were deriving a lot of differentiation formulas. Yes. So how you can write this? Can you say what comes in the Taylor series? What should come here? F prime of x naught plus, this is your step h. You can k, you can take. So it should be outside. Then, so here it is already f prime. So once you apply, it becomes f double prime. Plus so on, like the higher order terms equals to 0, right? We will neglect those higher order terms. So can you tell me what is h naught here? I told you that we are expecting the next is x1, like x0, we are the initial guess. Our next step or x1 should be such that we reach the minimum. That means x1 equal to 0. Okay. Then, so you already know. So for what step size that does that happen? I'm asking. For any step size, it cannot happen. So for a particular some step size, so can you give me the value of h0? We can compute the value of h0 from here. So what h0 is? Can you say it to me? What is h0? Just put it to 0. Ignore the higher order terms. Ignore the higher order terms. Can you check that you get this? Can you check that you are getting this? So can we further simplify this? I'm asking, can we further simplify this with something on the board? Something is already written. Can we simplify d not? Yeah. Can you further simplify? What you will get? You already know this quantity. You just put that in place of d. So you see that the denominator and numerator they cancel out. So you'll be left with the second derivative. So what does it give? 1 by f prime of x naught. Is it correct? Appears surprising, but true. Okay. That's the beauty of this method. Something unexpected will come just by applying common sense. Okay. Is it okay? Who did not understand? I'll repeat again. So okay. So now, like whatever method is, what's our method? Can we put the value of d naught here now? Can we put the value of d naught here now? So say put h naught in star and we get what? X of 1 equals to x of 0. Minus f prime x equals to x0 divided by f double prime x equals to x0. Is it clear? And this is our method for optimization. Okay. In general, if I write, so in general, if I write general method, this is a method equation, xk plus 1 equals to some xk minus, like iteration step, minus f prime x0. Yes, not x0 anymore, xk, f prime at xk. Yes. Third, we used one logic. We found a step size such a way that in next iteration, we will find our extremum or minimum. So such kind of methods, such techniques, which involves finding an acceptable step size, like finding an acceptable step size, are known as such kind of algorithm which use this technique are known as line search algorithms. Okay, line search. Okay, so Newton-Raphson is a particular method in those family of line search methods. There are a lot of line search methods. Newton-Raphson is one of them. Okay. So this method you saw here, this is a very nice looking formula which you have already seen. But the only difference is, we have f here. Okay. So this is a very general procedure. We will gradient based optimization, gradient descent also. When this method in 1D will extending to n dimensions, you will see the f prime here. I will replace it with a gradient. Okay. Like a Hessian or like something. Okay. So in multi dimensions. So if you have understood this method, that method will be more easier to understand. Okay. Those who found this method hard today, I will share the video. Go and watch. Okay. So yeah. So what are the limitations of this method? What are the hmm? What are the limitations of this method? You need function is differentiable. That's the drawback of this method. Okay. It is, but it requires a good initial guess. Okay. Yeah. Yes. So methods that avoid the drawbacks of the Newton method. Listen carefully. Like methods that avoid the drawbacks of the Newton method, and but behave like Newton method. Okay. So those who avoid the drawbacks of the Newton method, but they behave like Newton method, are known as quasi-Newton methods and will be covered by one of the groups. Okay. Like the BGFS method is one of the quasi-Newton method. Okay. That one of the group will cover. So I will be talking till here today, but I want to give an assignment. Let it be. Today's assignment, how many of you did? Many have done.